It's 3 o'clock, so I think we can start with the webinar. Welcome everybody who is joining this webinar. My name is Stijn Daniels and I'm the president of ICTCT. I think that most of the people in the room know a bit about ICTCT, but if you don't know it yet, please look at the website ictcct.net, where you can find all information about ICTCT and also can sign up for a newsletter that is not sent too regularly, but that always contains interesting information, among others, the announcements for the webinars and also announcements of events like our conferences. People who are interested to submit an abstract for our next extra conference that will be held in Winneba in Ghana in June. The call for abstracts is on the website available now. The submission deadline is the 3rd of February next year. And the topic of the conference will be enhancing traffic safety, prospects and challenges for a safe system approach on the African continent. So all people present today are very welcome to submit an abstract for that conference, and more practical information about the conference will also be available via the website. Then it's also the moment to announce already and to ask you to note the date for the next annual conference of ICTCT. It will be the 26th and the 27th of October next year in Catania in Sicily. And the call for abstracts there will be available in spring 23, and will also be announced as usual via the website and the newsletter of ICTCT. So we are here together for the webinar. Welcome Arend Schwab, who is an emeritus professor at the TU Delft in the Netherlands, and who has been working on the physical aspects of bicycling, in particular on bicycle dynamics, for which he also created a lab at his university in the years 2000 and 2000, I mean, and which he ran until his retirement in 2021. So we are very pleased to have Arend here today, that he can make a bit of time to give a lecture to us about his work that is obviously also related to bicycling, to safety of bicyclists, and of course to safety in traffic in general. So before we start the actual webinar, a very few practical things. We are about 80 people today who registered for the webinar. We will have offered the opportunity to ask some questions after the lecture. The lecture will be last around 40 minutes. Afterwards, we will have a quarter of an hour time for questions and answers, and we hope to finish the session around 4 o'clock. Just a reminder, this webinar is recorded. Everybody who registered gave consent to that. So you can also find back the recording of the webinar afterwards on the YouTube channel of ICTCT, that or simply the website of ICTCT, and we will make it available there. And then one last thing, if you have some questions, so Arend will start his lecture. If you have some questions, don't hesitate to put them directly, if you think about them, in the chat of this session. And then we will compile all the questions afterwards and give Arend the time to give a structured feedback on that, and also give the audience the opportunity to come back to these questions if there is time left also at that moment. Good, so I would say over to Arend right now. I will unshare my screen, and please, Arend.
Yeah, okay, thank you, Stijn, for the nice introduction. Let me get the technicalities. Can I get a confirmation on that you see my screen?
Yes, that's
okay.
Very
Thank
okay.
you. Well, first of all, let me start by thanking the organization to give me the floor for talking a little bit about bicycle dynamics and control. As Stijn already mentioned, I'm emeritus, but of course, as with most professors at the university, it's sort of my heart and my life, so I keep on working still a little bit on this topic. I have still PhDs running, and well, most of you know the works. So let me start actually by a motto. I have a motto for this presentation, and the motto is actually everyone knows how a bicycle is constructed, right? It's two wheels and a steering assembly, nothing much, nothing less. Yet nobody fully understands the operation. And with the nobody, I also include myself. Although I have spent now, what is it, 20 plus years on this whole bicycle dynamics and control. But don't let that discourage you. It's actually a fun topic. I couldn't have done this by myself. My co-workers at TU Delft, the whole list, but also Cornell University, because as you may think, this work did not start in the Netherlands, but it started when I had a sabbatical year at Cornell University, and I was babysitting my host because he had to write a grant proposal, and he said, please babysit me, because otherwise nothing will happen. And I was sitting next to him and I said, what shall I do? He said, well, actually, you're from Holland, you know about bikes. Why don't you look into this work we have done some time ago with some interesting results, contradictory with literature, and maybe you can make something out of it. And that turned out to be a lucky shot for me because it was great. Coming back to Delft, I started a bike lab. You could do that in those days without any grant money or whatever. And that grew into what's now called TU Delft Bicycle Lab. Two key publications on this topic, if you're for further reading. One is with the Proceedings of the Royal Society. That's about linearized dynamics equations for a bicycle. And the second one is in 2011 in Science on a bicycle can be self-stable without gyroscope and trail. And actually, we needed these publications as a building block for this whole lab and for getting eventually grant money. Bicycle dynamics. Let's start with an observation. Now, most of you, well, only the elderly people in the audience will know this movie, Jour de Fête by Jacques Tati. It's a movie from 1949, and it's about a postman who wants to rationalize things. And to rationalize, he uses a bicycle. You see a bicycle moving by itself, and everybody thought, well, this is movies, right? So everything in movies is a trick, so this must be a trick. But actually, this is not a trick. It can even go around the corner, as you can see. You need a slight banking, but that's a detail. Oscillation, and then the oscillation will die out. So I would call that super stable, right? And where do we know this stable behavior in mechanical structures? We know, well, if there's some damping in the structure, then it will be the oscillation will die out. But well, if you think about the bike and about damping, I mean, there's maybe some scrubbing at the tires and a little bit friction in the bearings, but there's not so much damping going on. So it's sort of for mechanical dynamicists, it's like a mystery. Where does this all come from? How does that work? Bicycles are a very old contraption, right? They were invented around 1800s with the velocipede and two wheels steering assembly, and then they were propelled by feet moving on the ground. But quickly people wanted to go faster. And I always say there's some gene in our GNOME, and that tells us faster. And that makes sure that every time you think, oh yeah, I want to go faster. Well, if you want to go faster, what do? They mount pedals on the front wheel, and then by pedaling, you can go faster than just pedaling on the ground. Moreover, if you want to go faster than that, then you have to just make the wheel larger, the front wheel, right? The larger the front wheel, for the same revolution, the further is the distance, so you will go faster. And of course, there's a restriction to that. Has something to do with leg length, and then you see a jump in the evolution, and you see a chain drive with a gear ratio. But it's clearly a evolutionary jump because the large front wheel is still there. Then people say, oh yeah, but this large front wheel is not necessary, and on purpose they show then a small front wheel. Then you see that the steering assembly is actually, the steering axis is too far away, and they have a contraption for the handlebars. And then the smart guy said, well, if we tilt the steering axis a little bit, and the handlebars will come towards us. And actually, that's the end of the evolutionary process. That's this safety bicycle, which is, which if you look outside, is still out there. And nothing much changed between the 1890s and now. And that's in itself is already interesting. Okay, in those days, around 1890, people wondered, of course, how does that work? Why does a bike fall over at rest, but given some forward speed stays upright? Where does this stability come from? And then in the UK, Whipple, and in France, Carvalho, almost simultaneously started research on this. And they made a very simple model. Not too simple, of course, but with the main ingredients. Rigid bodies, you fix the rider to the bike, you have no control, hands-free, the system is symmetric, you have idealized contact, point contact, no side slip, there's no propulsion or braking, and you're on a flat level road. And all in all, you come up with a system which has only 3 degrees of freedom, meaning the bike can move back and forth, it can lean left and right, and you can operate the steering assembly. You can steer, you can lean, and you can move forward. And note, all under these assumptions, it's an energy conservative system. There is no damping, there's no propulsion whatsoever. Now, this may seem like a hard set of equations, but actually it's a simple set of equations because it's just Newtonian mechanics. It's just mass times acceleration is forces. However, for our case, we have written it in a more convenient form where we take our degrees of freedom, the lean, which is phi, and the steering angle, which is delta. And we pulled out a number of variables which we think are important. Gravity, G, is an important one, and forward velocity, V, is also an important one, because we noticed that the stability of the whole system is highly dependent on this forward velocity. So therefore, we pull out that velocity variable. And then we present equations like this, some numbers for a specific case. We can investigate the stability of the motions, of this lean and steer motion at a given forward speed by looking at eigenvalues of the system, all very technical, not so interesting. The main message is Newtonian mechanics, equations of motion, from that we can determine the stability. And if we then look at that stability chart, and that is a graph which has on the horizontal axis the forward speed, because we find that a very important variable. It's unstable at low speed, stable at higher speed. And on the vertical axis, we have what we call the eigenvalues. They are characteristic for the motions. And when the blue lines, when the real part of these eigenvalues are positive, it's unstable, and that's the blue lines. And when all the blue lines are negative, then it's stable. And the red lines have something to do with the oscillatory motion of the bicycle, the frequency by which it oscillates. Well, looking at the graph, we start, of course, as we see, with very unstable motions. At 0 speed, we see positive eigenvalues, so the thing will immediately fall over, and that's exactly what we experience. But when speed increases, we see that all these blue lines become all negative. Therefore, from a certain speed on, this bicycle, this model of the bicycle even, this simple 3 degree of freedom model, this model will show stable motions. And we can check that, of course. We can do that in our multi-body dynamic software. We make a model and we simulate the motions, and we see at low speed, the thing starts to oscillate. Let's run that again. The thing starts to oscillate, and the oscillation grows and grows, and then the thing falls over and you crash. And actually, this is exactly what happens when you learn how to ride a bike, because you find bike riding scary, and you're not so good at it, so you don't dare to go so fast. But that's actually not a smart move, because when you go slow, the system is very unstable, and you have far more chance of crashing. So what should you do when you start learning to ride a bike? Well, you should speed up, right? And that's exactly what your parent does. He pushes you on your bike, so you have some real forward speed. And then when there's some perturbation, that lateral motion will die out, and the thing will get upright again and is stable. So clearly, this very simple 3 degree of freedom model explains the dynamics which we observe in real life on the bike. Remains the question, of course, where does this come from? That has been a long-lasting question. Now, I always say this self-stability is like some auto-magic control. So the big question is, how does that work? Well, that's a difficult question. So maybe let's go back to, how do we balance a bicycle? Now, I want you to take a second to think how you balance a bike. Usually when there's a live audience, I can ask the audience and they reply, but now in the chat, now in the online version, that's a bit more difficult. So I will pause so that you have time to think. I probably balance the bicycle by. Just fill it in. Now, to be honest, that's also a difficult question, because what you do is you operate the steering assembly, you lean with your body, and it's not that obvious what happens exactly. So let's go to a bit simpler problem and say, well, the bicycle is like an unstable thing. It's like this stick on my hand, right? Which can move, fall left or right. And how do we balance a stick on our open hand? Well, if the stick falls to this side, we move our hand quickly to that side. And if it falls to the right, we move our hands to the right. So when we just move the contact point in the direction of the undesired fall. And that is a way how you can balance such an unstable system. Now let's do that on the bike. In the bike, it's a bit difficult because you have to move the ground, right? You have to move these contact points. However, in a moving bicycle, you have a steering assembly. And if the bike is moving and you steer to the left, the contact points go to the left. And if the bike is moving and you steer to the right, the contact points go to the right. So with your steering assembly, you have a mechanism of moving the bike underneath you, such a way that you can balance. That also means, of course, that you have to do a very counterintuitive thing. So the moment you fall to the left, you have to steer to the left to get upright again. And the moment you fall to the right, you have to steer to the right to get upright again. And I believe that is not a natural way to do. And that's exactly what you observe when people have to ride a bike, start riding a bike to learn it. It's not a natural thing. You would say, oh, if I fall to the left, I steer to the right. But that's very counterproductive. Then you will fall even more. So learning how to ride a bike is an acquired skill. And this may be one of the reasons for that. Now, to demonstrate that really works, steer into the undesired fall, the main mechanism to balance. Students build a Lego Mindstorms bicycle. That is a small bicycle with 2 wheels and a steering assembly. There's a motor for propulsion. There's a motor for the steering. There's a sensor on top of it, and there's a controller. And then the idea was, well, with the controller, you can sense that the bike is falling over, and then with the controller, you can control the thing. Now, Joep Mutshuis was one of the students. He was doing this project, and he was a bit in a hurry, but he was a motorcycle rider, so he thought, well, I know how to ride a motorcycle. I know how to balance such a thing. But whatever control program he made into the thing, it didn't work. And he was in a hurry also to go to an internship in Switzerland. And then somebody said, well, there's a lab somewhere there at TU Delft in the back, and it's about bicycles, maybe you ask. And I said, well, Joep, actually, it's pretty simple. You have to steer into the undesired fall. So you have to measure that the thing is falling over, and then you have to steer in that direction. And how do you measure the thing is falling over? Well, you have probably some lean rate sensor, some nice IMU on the system. And then you have probably some steer motor, and it's probably a DC motor. So the voltage on the motor is proportional to the amount of falling. And it can be 8 or 80 or -8 or -80. That doesn't matter. It's a very simple law, and that should work. And then it was quiet for a second, and I said, okay, what is the problem? And Joep said, well, it's only one line of code in my controller. I said, yeah, okay. Well, he went away, and I think, what was it? 5 minutes later, he came back with this video. And the video clearly demonstrates you have to steer into the undesired fall. That is the way to balance your bicycle. And actually, if you look at the video in slow motion, the bike is falling and then it's steering. And the bike is falling to the right and then it's steering to the right. So in real life, you also observe this mechanism. So clearly, balance a bike, steer into the undesired fall. The next question is, of course, yeah, but the bicycle can do it by itself. It has, as I said, auto magic control. Where does the magic come from? What makes it steer in that undesired fall? And almost like everything in life, there are two groups. The left and the right, the blue and the red. And in this case, they are called the gyroscope people and the trail people. Now, what are the gyroscope people? Well, they say the bicycle has a rotating front wheel. And that's a rotating wheel about one axis, and that's falling about the second axis, and that gives a torque about the third axis. It's like a gyroscope. Gyroscopes are used to obtain fixed orientation in space, to create torques in space. It's a known concept. Well, then the other people say, the trail people say, no. It's only a minute contribution, these torques, due to the gyroscopic effect. And on the right, people say, no, it's about the steering geometry, that the steering axis is tilted a little bit, and then the contact point is behind the steering axis, and then you get something like a caster wheel, like in a desk chair or a shopping cart. And because that contact point is behind the steering axis, you have this self-stable motion. Well, there's only one way to solve that, of course, to math, prove it. Well, the people on the gyroscope were supported by Klein and Sommerfeld around 1910. These are half-gods, they live up somewhere. They lived up somewhere there. Sommerfeld was nominated 81 times for the Nobel Prize. Klein, famous from the Klein bottle. And together with Fritz Noether, the brother of Emmy Noether, they wrote a 4-volume set of books, more than 1,200 pages, on Theorie des Kreisels, which means a theory of gyroscopes. And of course, if you write a book on gyroscopes, then everywhere you look, you see a gyroscope, right? And they looked at the bike and said, oh yeah, there's the gyroscope. Of course, they knew their classics. They knew the work by Whipple and Carvalho, and they went to the derivation to show that it's eminent that you need this gyroscopic effect, otherwise it cannot be self-stable. Unfortunately, my colleague Jaap Meijaard followed the whole derivation, and he found 2 sign errors in the derivation. And well, if you fix for the sign errors, it's not so clear that if you kill gyroscope, then the thing is always unstable. So could be self-stable without gyroscope. Then the other, the red and the black to left and right, the other one, the trail people say, no, it's the steering geometry, which is very important. One of them was Jones in the 1970s. He's from the UK, from Cambridge. He had his PhD in chemistry, but he was very interested in bicycle dynamics and control. right? What makes it so easy to control a bicycle? And that focused him on this self-stability. And he believed in this whole world of trail, of contact point behind the steering axis. So he built bicycles where the trail is very large. And then well, first of all, he knew his classics. So he knew about Klein and Sommerfeld from the 1910. And in the top, you see a picture. He rides without hands. He mounted a counter-rotating wheel on the front assembly, such to kill the gyroscopic effect. And then he had an experimental bike with no gyroscopic effect. And he said, oh, look, mommy, I can even ride without hands. So the thing is still self-stable almost. So that's not the thing. But the moment he started to tinker with the trail, with that contact point behind the steering axis, he discovered suddenly that very large trail, it was rather self-stable, easy to ride, with a negative trail, so the contact point in front of the steering axis. Then it was he couldn't ride without hands, and it was very hard to control. He went into a derivation with potential energy to show that trail is the most important factor for the stability, a necessary quantity, even positive trail. However, he used potential energy, and potential energy for a moving bike or a stationary bike is identical. And if you take in the whole dynamic model, it's still not clear if you need positive trail to be self-stable. So we are still remained with the question, what makes this bike self-stable? Which automagic thing is it that is necessary, a necessary condition for the self-stability? Now, if you look at the bicycle in itself, I said, well, our model is very simple. It has 3 degrees of freedom, lean, steer, and forward motion. However, the parameters which define a bicycle, meaning the wheelbase, the head angle, the mass distribution, those parameters, they are approximately 25 in total. Meaning that the family of bicycles with these 25 parameters is very large. You can think of all kinds of contraptions in that sense. So you have a lot of variables. If you then want to investigate the effect of these variables on the stability, you can go through the math, and you can, for instance, write down out these equations to find out in which case is the thing self-stable. But you end up with a set of equations by which you can paint almost the wall of the university. It's undoable. It's an undoable task. So we have to simplify even more. Now, what we did is we simplified the bike by having all the necessary ingredients, and it's called the two-mass skate bike. It has a rear frame, it has a front frame, it has idealized point contact, it has no gyro because it's on skates, it has no trail because the steer axis really hits the ground at the contact point, and it has only 8 non-zero parameters. And with these parameters, we could mathematically map out this stability thing, and we could find regions for which we say, oh, this machine should be self-stable. So without gyro, without trail, self-stable. And on the right, you see a figure. Again, horizontal forward speed, vertical is stable or unstable. And from this speed of 3 meters per second, the thing should be self-stable. Without gyro, without trail. Of course, we built the thing. We went to the gym. We propel it. We bring it up to speed. We release the machine. And then it stays upright. But of course, it should be really self-stable. So we should also be able to perturb it. So we bring it again to speed. We hit it sideways. And as you can see, it oscillates, oscillation dies out, and it's still upright. So clearly, this is theoretical and experimental, the verification of a bicycle can be self-stable without gyro and without caster. And actually, this was really needed to set the bicycle dynamics research on the map. Because before these publications, when I said, well, actually the whole thing of dynamics and control in a bike is important, people said, yeah, ha, ha, ha. Bicycles are more than 100 years old. Come with something new, nanoscience, MEMS, or whatever. I said, no, there's still an interesting thing. This was our building block. This is what we need. Some of this material can also be found in a shorter and maybe more pleasant presentation. Later on, Minute Physics made a nice video build on this. And Veritasium also made nice YouTube movies on this to spread out the news and to show. And it's in the presentation. I think the presentation will be shared afterwards with you, and then you can look this up. These are nice videos. We cannot make such nice videos. They're cool. Okay, let's now get to traffic safety, because there's a rider on the bike, right? And the rider is doing control. And he experienced some bicycles can control better than others. Some bicycles handle better than others. Some bicycles even handle very unsafe. I know from experience, for instance, if I ride my folding bike, I find it dangerous to ride with only one hand on the handlebar. So if I have to stick out my hand, it's a dangerous maneuver already. And of course you could say, oh yeah, but that's obvious. It's a folding bike, so these have these small wheels, right? So that's the whole problem. Well, here I like to correct myself or you. No, that's not necessarily the case. By changing geometry things, changing mass distribution, we could be able to make a bicycle which handles, a folding bike, which handles approximately in the same way as a normal bike. Unfortunately, they did not do that yet, but those are the options we have. Okay, to understand why does a bike feel so much different, one bike feels so much different than another bike, we have to think about how do we control the mostly unstable bike. You see two pictures here. One of them is, of course, famous. That is my daughter, because I used her to study how do you learn how to ride a bike, how do you balance, how do you do it. Intermezzo. Let's test your knowledge, right? Because I think everybody can ride a bike in the audience. So you're all an expert, without doubt, right? You're still alive, so probably it worked for you. To turn to the right, you have to steer. What do you do? If you want to go right, what do you do on your bike?
To right.
Yeah, you turn to the, of course you turn to the right. That's the whole purpose, right? You want to go right. Well, actually, it turns out that you have to briefly turn to the left and then just let go. And that sounds like a crazy thing. Like, I want to go right, then I have to steer left. Now, what is the whole idea behind that? Well, let's show, first of all, let's show a video to do that. Those videos start, please. Yeah, let me go back. This was the original video. Yeah. So here I move, I steer to the left and the bike falls to the right. Now, of course, you don't see that I steer to the left, so let's do it in slow motion. Again, a simulation. I move the bike forward. As you now can see, I steer to the left. And then, of course, the bike falls to the right. And that's exactly what we want. If we want to go around the corner to the right, what we need a roll angle to the right. Now, how do we create that roll angle? How do we get ourselves in this leaned position? We cannot push against other riders. That's, well, not allowed, I would say. They don't like that, right? There's nothing you can push against. So how do you get this leaned configuration? Well, as we saw, this steering assembly moves our contact points. So if you want to fall to the right, you have to steer to the left, right? So you steer to the left, you fall to the right, and then you will feel on your handlebars that you will get around the corner, almost automatically. Now, I challenge you to do an experiment with this, and that is, it should be like a bit of an open space, not too much other traffic. You just ride straight ahead, and then you want to make a turn, left or right. Let's say you want to make a right turn. Instead of holding really with your hands on the handlebars, use your open hands pushed against the handlebars. And then you really feel what you are doing. Then if you want to go right, push a little bit with your right hand so the steering assembly goes to the left. And then you will feel the bike fall over and you will make a turn to the right. And it's a very very enlightening experiment, actually. Another story is maybe which you can connect to. We all know that if we are very close to the curb with our bike, let's say the curb is on our right, we are non-UK, so we ride on the right and the curb is on the right. If we are very close to that, that feels dangerous. And why does it feel dangerous? Well, to get away from that curb, to move to the left, you have to steer to the right, right? So you have to steer against the curb. And it's something we unconsciously know. Therefore, we find that so dangerous, so close to the curb. Okay, then again, the question was, how do we steer and balance? In the 70s, there was research on that in the Netherlands. And it was initiated by the government because the question was, is it dangerous to ride intoxicated by alcohol or drugs on a bicycle? They wanted to do experiments, but on the open road seemed to be a bit dangerous. So they made a bicycle simulator, which you can see on the right. And then a whole setup where they can measure the rider control, how well can you still control the system. And of course, we needed volunteers, but that was not a problem. People were lining up for free alcohol and drugs. And the outcome of the result, the outcome of the research was, of course, yes, you are not so well in controlling a bike when you are intoxicated under alcohol or drugs. So from that moment on, it was not allowed. After that, nothing much happened in bicycles research control, but motorcycle control even more, because in the US, the road authorities actually thought that the motorcycle is dangerous. So should we ban a motorcycle because so many accidents happens? And then David Weir started to do a theoretical research, and after that experimental research, to look into this rider control and the effect on the design of the bike, and to also show that the motorcycle is not inherently unsafe. But bicycles, after the 70s, nothing much happened. We were interested in how do you control? How do you steer? Do you lean? Because people said, oh yeah, I lean with my body and I steer and I feel this and I do that. And so what do? Research. We cycle on a treadmill. We put all kind of markers on us that we can measure our motions. We cycle on this big contraption thing at various forward speeds. We measure the motions. And we can, on the right, we can reconstruct them, and then we can pull out all the different things that you are doing. And then it turned out to be that if we order the motions in magnitude, order of magnitude, then the first motion is the bike is leaning and steering, and it's a coupled motion. That's on the left A. The second most important motion is that you are swaying, your heading is changing. The third one is that you are pedaling, that your legs are going up and down. And then you have your twisting of the body, then leaning of the body, and then steering. But all these motions depend on forward speed. And we noticed, for instance, that at very low forward speed, yes, you use your body, your knees to balance, what you may observe also in real life. But at higher speed, you only use your steering assembly to balance. So then we knew, okay, we have to focus, if we look at rider control and handling, we have to focus on this steering control. Now you may ask, what is the relevance to cycling safety for all this? How does that connect to our society? And of course, as your audience, you know all that in traffic, we go for mission zero. And that for cars that works, the number of seriously injured in traffic go down, and also deaths in traffic for cars. But for cyclists, it goes up. Both the number of deaths and both the seriously injured go up. And yes, of course, it has to do with exposure. People are getting older, more elderly are on a bike. But notice these are single vehicle accidents. Most of them, 75% are single vehicle accidents, meaning that they just fall over with their bike. It's not that they get run over by a bike, but they just fall over. And in this falling over of a bike, the handling and control plays an important role. So we were interested, can we improve that? We did a number of studies for the consumer industry. First of all, we looked at safety of regular bikes versus e-bikes and elderly? Do they behave different? Do they show different control? We also applied our knowledge in sports engineering. I'm not going to talk about that. And one thing which came out of the research was, can we not help the rider in balancing a bike? So if you say, well, to balance a bike, you have to steer into the undesired fall, that's an assignment the rider gets. But can we not buy a mechatronic system which does that already? So which makes the system stable? And yes, you can. So we made a bike which is called Steer Assist. It's not taking over full control. It's helping you in balancing. And you can compare it like lane assist in a car, which nudges you between the lines. The moment you try to veer off, it nudges you back again. And the same is with the steer assist. The moment you fall to the left, it starts steering to the left. And the moment you fall to the right, it starts steering. And so it gently nudges you into the corrective and direct steering action. It feels like a regular bike. People sometimes have some trouble that the bike is doing things and then they want to fight that. Well, you shouldn't fight it. You should go with the flow, of course. And we could prove that the shared control that released the human a lot from the control task. Then there were various other projects. We always have been interested in a fixed base bike simulator, where we can in a safe environment do all kind of experiments about handling and control. We start with a fixed base with forces on the handlebars as a feedback. Then we added, of course, virtual reality with a head-mount display. As you can see, this is a fixed base one. It does not have leaning in it, and I always call it the bicycle simulator with the bucket, because a lot of people get sick on this. So you definitely need this lateral motion. And we're now in the process of even building one with lateral motions, but it's a tricky thing. As we know from car simulators, you should not try to simulate everything at the best. Maybe everything should be a little bit less accurate. Other things are that bicycle manufacturers have trouble. On the left, you see bicycles which show unstable shimmy behavior. And that's a local phenomena which has to do with high speed instability. It arises when the bike has a not so high torsional stiffness, and they needed guidelines for designing. And on the right, again, a sports application where we want to assist riders to make a fast and safe descent in cycling. Because up until now, in the elite teams, when they were cycling and there was somebody who was not a good descender, then the question was always, well, how can I learn how to descend? And they say, well, just follow that guy. He's good. Follow him. Yeah, well, follow him. What should I do? Well, follow the guy. And that's not the way to go. So we measured and found out that there is a profound different behavior in this fast descender opposed to the slow descender. And of course, it has to do with braking, but it has to do also with the way he's braking and the moment and the amount. And that's something you can train cyclists on. I think time is running out. There are various more projects which I love to talk about, but let's give the floor to questions. I think this gave enough rise to questions. I will stop sharing now. How do I do that? Yeah.
Thank you, Arend, also for the nice videos. And yeah, let's start the questions. Who wants to start?
Yeah. So the procedure is like that. Please write your name in the chat, and I will just follow the queue, but you would be allowed to use your microphone and show your video so that we can have direct communication. But as a warming up, Arend, I had a discussion with quite high level person from Cycling Europe, like one of the biggest cycling producer in our region. And basically what she told me was that the current price of electrical bikes, about 2,000 euros, that's kind of how far the customers want to go. And it's very little more they can do for bikes. I mean, they cannot put more electronics because then it's becoming more expensive. So my question for you is, what is the next low-hanging fruit? What is simple enough but still can be usable and improve stability of bicycles?
You mean to improve cycling safety or to improve the stability of the bike?
Well, of course, I'm more interested in safety, but generally to improve bicycle as a vehicle.
Yeah.
Any dimensions, comfort or whatever, stability, safety.
Yeah. Well, I think
not that much cost.
I think the low-hanging fruit is to step away now from what is what, as I showed in the beginning, is this bicycle evolution. Like, oh yeah, we always have a head angle of 72 degrees, and we always have a trail of 8 millimeters. That's how we design bikes. That's how we like them to ride. To step away from that and use our scientific approach by just looking at objective numbers like stability index, handling index of these bikes, and then change the design such that it helps elderly rider to have a more stable bike, and the younger one to a more agile bike to fit the bike to their demands. And that is not done yet. And my biggest example is always, in that case, this folding bike, which folds wonderful. I mean, it's a wonderful machine. Today I even still I used it, but it doesn't handle so well. And we can do better. We can do better there. So the low-hanging fruit is put more of this science into the design world of the manufacturer. But that's difficult. That's difficult because they have other problems. They have structural dynamics, structural problems, and those kind of things. Yeah.
Okay, thank you. Harry, do you want to say your question yourself?
Yes. When we look at the car industry, I mean, people, they want to pay amount of money for the fifth star in the NCAP, and I think if we developed an NCAP for bikes, maybe we could overcome the struggles about people don't want to pay for a safe bike. What do you say to that?
Yeah, that could be a route to go. I know, for instance, that Bosch e-bike systems is very focused on safety, and that was also one of the reasons why they wanted to develop for their bikes this ABS for their bicycles, to have safe braking, and that fits, and together with this steer assist and the ICT IoT modules in bicycles, which detect that the bicycle has crashed and then sends a message to the first aid, etc. Those things that I think they can help to give more safety to the system, and people are willing to pay for that. Absolutely, yes, yeah, I agree.
Okay, good. Then we have Jean Hevel. Can you?
Yeah, thank you. It's Jean. It's a French Jean.
Sorry.
No problems. Yeah, it's just when the technical question when we see the debate is not settled on what's contributing to the self-stability of the bicycle, and especially with the practical kill of bicycle and rider. You talked about energy, about the derivation of the equation from the 19th century. Is there a torque approach where you can break down the different components? Because I assume it's a accumulation of different things, and that's why it's so hard to identify exactly what works. But to see the magnitude of the respective contribution and then take an analysis from that point. Thank you.
Yeah, Jean, I understand it. I understand what you say. Look at these different contributions. That can be done. However, if you look in detail to how the stability analysis works, it's just in the end you come up with some fourth order equation for which you have to determine the roots, and if the roots are positive or negative or imaginary, that determines the stability. So yes, you can look at the different contributions and you can check, do they help in balancing a bike? So do they have the right sign for steer into the undesired fall? And how much is that? But if with that you could say, oh, then if this works more than that, then maybe we should focus on this instead of that. So that's true, yeah. And again, a design bureau could use that. Yes. Good point.
Mm-hmm. Okay, do we have any more questions? Okay, I can fill in while you are writing, I hope. A question about, yes, Jan, I see it, but I will just finish mine. You mentioned that you are building a bicycle simulator.
Correct.
And we also have been experimenting a little bit with virtual reality bike simulator.
Yes.
And one of the big questions was like, what do we really want to study in that environment?
Yeah.
Because like you cannot study dynamics because it's not realistic enough. But what would you study?
Okay, a nice question, Alexei. So currently we are working on our next generation bicycle simulator, which has a very specific task. We are building it for the University of Groningen. And Groningen had a specific question. They said, can we assess how well elderly can mount, dismount, start and stop, and move into traffic? So those three questions. And with those three assignments, we started to say, okay, we can start by building a simulator on which you can mount and dismount, on which you can start and stop riding, moving around in traffic. Okay, let's wait and see. We'll do our best. So yes, by very specifically defining the tasks we wanna assess, we are able to build something now. But I think from the other way around, saying, oh, we want a bike simulator, then you can simulate that you're biking. And the whole general picture, that is deemed to fail. And I think you already see it in car simulators. People have difficulty in estimating distance, in estimating speed, and on the bike, that's even more difficult. Yeah.
Okay, thank you. Jan Andersson, VTI.
Yes, thank you, Alexei, and thank you for a very nice presentation, Arend. I come from another perspective, how the riders actually ride the bike. And when you have this perfect example, you don't want to steer into the curb. You have to go to the right before you go to the left.
Yeah.
But I was thinking, do they actually do this, or do they just lean a little bit to the left, and then, as you have a nice example, then you have to steer more into the left instead?
Good question, Jan. Yeah, good question.
Yes. So it's a combination of, okay, this is the stability of the bike, but how do the riders actually perform the task?
Actually, we had the same question, of course. And first of all, I like to challenge you. Go to an open space, the parking lot. You have enough of that at VTI. So go to an open space. It should be a dry day and no snow also. So. And then you make a puddle of water, and then you ride with your bike. You first ride through the water, and then somebody at the end says left or right. You don't know what he's going to say. Yeah. And then you do what you want to do. So you say, like what you said, now, look, no, I lean this and then I steer. Yeah, whatever. Yeah, it doesn't matter. And then in hindsight, look at the tracks on the ground.
Right.
And you will see always that what you will do if it was right, then you will see, oh yeah, I veered to the left and then I went to the right. You will see that steering always happens. It's the only way. And maybe one of the explanations is also in the system where you have a person and a bike as a one system. Of course, you have this relative motion of the upper body relative to the rear frame, but there's only a line of contact. So there are no torques which you can apply. So if you do your upper body to the left and the bike goes to the right, and the net result is very low. So the lateral force in the end, which you get at your contact points, are not so high.
Thank you. I will definitely do that.
Please try.
Yes, absolutely.
Please
Thank you.
Yeah. You can also do it in the snow, by the way, of course, because then you see the tracks, right? But be careful.
It will yes,
be careful.
Thank you.
Okay, great. Anna?
Yeah, hi, Arend. Thank you very much for your nice presentation. I was just wondering if we could elaborate something about how road friction would affect the self-stability and more or less like you had the optimal speed for the self-stability, if that's affected by the road friction.
Well, yeah, in that sense that it may be a bit of a stupid answer, but you need enough friction, please, because the moment, as you know from the moment you lose contact, then you're lost. Then it's really gone. So, and especially for the front wheel, the rear wheel is you can still recover from that, but for the front wheel, you need really no lateral slip. And I think that is the whole problem in cycling with only these two contact points on the road. Now, there are some solutions for that. So, for instance, with a Piaggio, the motorcycle, you have two front wheels. Then the chance that both wheels lose friction on the front is, of course, not so high. I mean, so and they also feel safer. That's what people say. They feel safer to ride. But yeah, that is one of the biggest problems. That you need enough friction on the front wheel. And we all know from experience. I mean, you in the north know, of course, from the slippery conditions. We here also, we don't have so much snow and ice anymore, but we do have leaves, and from the falling leaves from the autumn, which makes it slippery. And yeah, you need enough friction. That's the whole problem. And there's no way I studded tires, but yeah. And we see, by the way, oh yeah, maybe I can connect this. We see an interesting move nowadays in tires. Of course, the tire makes the road contact, and that helps you in creating enough friction. We see that people are using more wider tires nowadays, and they say that's for safety reasons. And I can agree on that, because they are what we say more forgiving, and they deform easier. They have a larger contact patch, and the rolling resistance is still okay. It's not really higher, and you can go through a whole analysis to show that it need not be any higher. But you have a larger contact patch, and that helps you again in getting the most out of the available friction. And then you can have that part of the contact region is slipping, but still the other part is still in contact. And that's important, of course. So wider tires really help.
Okay, thank you.
Okay, we have a follow-up question from Matthias.
Yeah. Hi.
Hi, Matthias.
Hi, I'm Matthias, also from ITI. I have noticed from my own biking in snow and ice conditions in Sweden that I can get better stability in curves if I move my point center of gravity outside the bike, so that I don't have to lean the bike. And I suspect that the large camber with tires on ice and snow gives you a worse grip, and I can.
Yes.
And I think I've seen professional racing drivers doing that as well in curves, also on high friction.
Correct. Yes, that's absolutely correct. Yeah, you're right. That's also what motorcycle riders do at the GP, as you can see, right? They want to keep their bike as upright as possible, but you need that center of mass to be down. So the only way is then move relative to the bike. Totally correct. Yeah.
Yeah. So I just want to point out that maybe the behavior of the bicyclist changes a little bit when it comes to low friction also.
I know it changes. I know it changes a lot, because from experience in my colleagues and friends in Finland, they learned some years ago. They learned. They taught me how to go around the corner safely on very slippery surface, and so they learned me how to drift, but it's a very safe way to go around the corner. It's only an acquired skill, right? You have to put out your. I want to go to the right. Put out your right feet, brake the rear wheel so it locks, and then you swerve around the corner. But you will not lose lateral contact on the front wheel, and that's the most important thing, of course. Yeah. No, I love that. I love it.
Okay, thanks.
Okay. I think that would be the last question because time is running out.
Oh, time's going quickly. We're having fun.
Yes. So it's Anya from Germany. I don't remember now your new university, the name. But the follow-up on that, having two wheels on the front.
Yeah.
So do we have our tricycle, the three-wheelers, constructed in their own way? Should it be two wheels in front?
Well, yeah, it's a good question. We see a nice, well, first of all, people always say, well, why you have a bicycle? Why not a tricycle? That's far safer and, well, it's statically stable, but going around the corner is very dangerous, of course, on a tricycle, on a non-leaning tricycle, because you do not have the option to lean into the corner. You will fall out of the corner. So therefore, you want a tilting tricycle. And this tilting tricycle, currently at Delft, we are making again one. This tilting tricycle can either have the wheels up front, the two wheels up front, or in the back. It doesn't matter so much. It more has to do with how complex become the construction, because if you have them in the back and you have your propulsion on the back, then you have a tilting, leaning, press propulsion on two wheels, complex mechanically. If you say, no, we put them on front, then you have tilting and steering, which can also be complex, especially when you think about braking these two wheels. And so it's a challenge for the mechanical engineer to design it, but you can either do it front or back. It doesn't matter so much.
Okay, thank you. Stijn, would you round up?
Yes, thank you, Alexei. Thank you, Arend, for this nice lecture. Very informative, I think, for most of, if not all of us. Very pleasant to follow as well. You also kept very well the timing, so thank you for that as well. Thank you also to the audience. Very interesting questions, and I think this is a topic that really needs to be followed up in the future by researchers and by the research community in general. So wish you all a very nice weekend. Thank you for attending, and see you soon at one of our other activities.
Thank you, Stijn. Bye. My pleasure. Bye.
Bye.
See you.